Yes, computer. Thank you. So, well, now that we're recording, hopefully you guys are seeing a lot more energetic than I have been for the last couple of weeks, and I should be catching up on all of our assignments very soon. So anyway, all right, questions on this supplemental information? Okay, we're going to cover all the rules we already haven't covered today. So I wanted to just get that out there as a, oops, not that. Come on. All right, do it your way. There we go. All right, let's get back to where we were and take roll. And the lower be coming on. So I actually took these tables out of a different book, but I found them to just be so much better than the summation in our book that I thought I better share them, because I thought this was a much better, condensing of all the instruction. So I think you'll find this easier to follow, but the book does have, all of that information. And then we'll get on to that. Everybody got the QR code? All right, moving along to where we were. Okay, so the summation of the nomenclature so far is find the longest chain, okay? And that's the longest chain of carbons. If it's other than a carbon, we don't care, okay? Then put our substituents on it, name our substituents with the lowest number possible, okay? All right. Questions on any of that? We're gonna do a couple more examples of these. So I'm going to switch over to, if you'll let me. Nope. All right, I'm going to switch over to blank 2. Okay, so we're going to apply every single rule we had so far in our system. We're not going to change the alkane. We're just going to apply all our rules. All right, so obviously the chain isn't the straight part. So we have to figure out what our parent hydrocarbon is. So let's see, we have 2 carbons here, 1 carbon here. So I think we should start numbering at least the first one. 1, 2, 3, 4, 5. And if we went this way, we'd have 6, 7. But if we went this way, we'd have 6, 7, 8, 9, 10, 11. So I think we're going to go that route. 6, 7, 8, 9, 10, 11. Okay. Did you also see that I trickingly went to a starting point where there was a substituent pretty close to the end? Because if you see there's a difference between one long end and the other end, and the substituent seems to be closer to that one side, chances are you're going to have to number it from that side. So you can like skip the step of numbering it in both directions. So I think we have a C12, a C11 chain on our system here. And so that would make it what? I really like this one. I love the sound of this word. It's 1 plus 10. So it's un decane. Un decane. Un decane. So there you go. It's 11. 1 plus 10. And so dodecane is 2 plus 10. Tridecane is 3 plus 10. So those are easy to remember. So now we have our parent. So we're going to write that down. Un. Oops. Wow. Getting better, but not there. Okay. Decane. Okay. So what I like to do is I like to just write them down first, and then we can put them all in order later. But I just want to see if we have it. So that's our numbering system, and that's our main chain. So now let's identify our substituents. Okay. So if this is our first, ooh, oh. Undo. There we go. And this is our first substituent. This is our second substituent, and this is our third substituent. Let's just double check, okay? It would be 1, 2, 3, 4, 5, 6. So that'd be on the 6 carbon no matter what. This is going to be on the 3 carbon down here. So I think that's where we're going to start, right? So we have a methyl group on the 3 carbon. So we have a 3 methyl. Okay. We have an ethyl group on the 5 carbon. So we have a 5 ethyl. And we have a methyl group on the 6 carbon. So we're going to just make sure we don't forget it by putting it here. And now we can apply the di-tri-tetra rule. And we have 2 methyl groups, so we can say it's dimethyl, okay? So we can now say, instead of that, it's going to be 3, 6 dash dimethyl. Now let's put it all together. The substituent goes first. Which substituent goes first, the dimethyl or the ethyl? The ethyl, because we don't count di, tri, and tetra. So we're going to start with 5 ethyl, 3, 6 dash dimethyl, un decane. Oh no, they get very long. I pulled up one of the things, like it's a steroid, and it's like 5 lines long on that pharmacy paper that's like wafer thin or paper, thinner than paper. So, okay, do we see how we applied every single one of those rules? And these are our basic rules for naming our nomenclature, okay? Yes. Okay, in the case here, this is our squiggly line. This is our long chain, right? So this is only 1 carbon off that long chain, so that's methyl. 1, 2 carbons off the main chain, that's methyl ethyl, which was 3-dipropyl. And then that's also just 1 carbon off the main chain, so it's also methyl. So that makes up 2 methyl substituents plus 1 ethyl substituent. It's funny, I unfortunately read a comment on YouTube about one of my other classes, and the guy says, "Why is this guy wearing a mask?" It's like, I'm actually live in person, but okay. All right, so done with that. All right, let's go back to where we were. Now we're going to complicate things slightly because not every chain is in a straight line, okay? So we have to assign them cyclo. Now, one of our rules is you include iso and cyclo in alphabetization. So I'm going to talk about cyclo. All that cyclo means is that you have a ring of carbon-carbon bonds, okay? So when we look at a hydrocarbon and we count up the number of carbons in them, I'm going to do 3 right here. We have 3 carbons, but we have 1, 2, 3 hydrogens, 1, 2 hydrogens, 6, 7, 8. So we have 8 hydrogens, okay? If it's a straight chain, it would have 3 carbons and 8 hydrogens, which means it has a general formula of Cn, so N being the number of carbons, and H, 2N plus 2. And again, being the number of carbons. So that tells you that the ratio of carbons to hydrogens, okay? And when we look at that ratio of carbons to hydrogens for propyl group here, we see that it has C3H8. And so that means that if this is 3, it'd be 2 times 3 is 6 plus 2 is equal to 8. So all straight chain hydrocarbons without double bonds or triple bonds follow that formula. CN H2N plus 2. Now, the reason I wanted to draw attention to that is because if we took 1 hydrogen off of this end of this and 1 hydrogen off of this end of this and turned it into a ring, our new formula is going to be CN H to the 2N. Because we took off 2 hydrogens and added a carbon-carbon bond. Okay, so, and that would give us this down here. Okay, so the smallest ring we can have is with 3 carbons, because 2 carbons is a line. So we have 3 carbons. So cyclopropane is the smallest one we can have. Okay, and so we have the cyclopropane, it's all one word, no capitalization. We move up to 4 carbons, it's cyclobutane, 5 carbons, cyclopentane, and if we had an 11 carbon ring, we'd call it cycloundecane. Okay, questions on that? Okay, so that being said, what if you have a substituent on a ring? Well, the cool thing about it is, let's draw a ring. Okay, so first of all, what is the parent ring? Cyclopentane. We have 5 carbons on there and cyclopentane. If you have one substituent on a ring, that's automatically on the 1 position. So you don't even have to say anything. But the proper name would be 1-methyl cyclopentane. Okay. Now, there's a rule. If you have 2, you want to have the 2 groups on, you have to figure out whether they're on the same side of the ring or different sides of the ring. Yes, they're cis and trans because of which side of the ring they're on. But let me draw a side view of it to get you to see that. Hang on. Hang on. There we go. Okay. So if we have 2, we have to say, okay, we have to figure out where they are in space. Okay. So if I drew the cyclopentane like this, it actually has a hydrogen here somewhere. Okay. But we have to figure out kind of where they are in space. So what I'm going to do is I'm going to put a hydrogen here and a methyl group here. Okay. But is that a real representation of this? Those are kind of flat, aren't those tetrahedral bonds? Okay, well, let me redraw this same one, and I'm going to redraw it where we have the unsubstituted side going back away from us. These 2 bonds are going to be coming toward us, and we're going to have a hydrogen up and a methyl group down, and a hydrogen up and a methyl group down. Okay, so now, if we look at it on edge, the 2 hydrogens are on the same side of the ring, and the 2 methyl groups are on the same side of the ring. Okay, because we cannot have, well, yeah, because in our structure here, they could be either way. So what do I mean either way? Well, I can actually draw it where the methyl groups aren't on the same side. Again, these are coming out at us, and the methyl group's going to be up here now, and the hydrogen is going to be down here, and the methyl group's going to be down here like before, and the hydrogen is going to be up here. Do we see on this one, one of the methyl groups is on the top of the ring, and one of the methyl groups is on the bottom of the ring. Okay, and that's this one right here. And on the other one, we have both of the methyl groups on the bottom of the ring. So see, they're opposite here and on the same. If they're on the same side of the ring, we're going to call that same or cis. And if they're on opposite sides of the ring, we're going to call them trans, opposite. Okay, so, but this is the first time we've had to deal with 3D perspective, except for learning that the tetrahedral was facing, had bonds pointing back and bonds pointing forward. Okay. So we have 2 possible isomers available to us in cycloalkanes. because we don't have the freedom of motion of the ring anymore. We've restricted it, so we now have a top and a bottom. And so we have to assign that as a top and a bottom. Okay. So that gets us into our first set of stereoisomers. Now, what does stereo mean? Stereo means space. It does not mean left and right. You know, so what it does mean is it means in space. And so that means that those two methyl groups are fixed in space. And we have to locate them in space accurately because we could actually have two different compounds. In fact, these are two different compounds. They have two different melting points. They have two different boiling points. But now we have to find out where they are fixed in space. So another way to draw this would be to have it done where we look at it in kind of like that same perspective where this is coming out at us. But instead of drawing them out at angles, what I'm going to say is that the hydrogen and the methyl group are just going to be linearly associated with each other here. So if I were to draw this isomer this way, is it easier to see both methyl groups are on the same side of the ring? And if both methyl groups are on the same side of the ring, that makes it which isomer? So let's do that same kind of different, slightly different perspective drawing where we have the H here and the H here and the CH3 over here. And again, these are our thicker bonds here sticking out at us. And it makes it easier when you do the straight lines to show, oh, there's definitely a methyl group going up and a methyl group going down. They must be on opposite sides of the ring. Therefore, they must be our trans isomers. Questions on that? Picture, is this the cis isomer or trans isomer? Or picture, what's the name of this? This is the 6-cis-1,2 dimethyl cyclohexane pentane. Or this is the trans 1,2 dimethyl cyclopentane. So what if they're not right next to each other? That's where this kind of drawing system works really well for us, because let's say instead of being right next to each other, we had that methyl group way over here. And it'd be really hard to figure out which side it was on unless we drew it in this perspective. CH3. Is this the thing where you note 60 degrees each time it's eclipsed? No, we're not there yet. That is, that's coming up. So if I have it here, we no longer have it in the 1,2. This is now the 1,3 isomer, because this is going to be our 1 spot, our 2 spot, and our 3 spot. We can still see that the methyl group is one of them facing up and the other one's facing down. So now it's our which isomer? When I redraw it, it's now our 1,3 dimethyl trans isomer. So, questions on that? Same side of the ring, cis, opposite sides of the ring, trans, no matter which position they have. So let's name some more cyclohexanes. Okay, so in the case of any substituent, like let's start with this one. Oh, actually, let's do that. So the first thing I want to note here is that the cyclo group has more carbons in it than the butyl group, right? That means the cyclo group is our parent compound. If the cyclo group had less carbons in it than the substituent, the longest chain, it would be a substituent. So that's the one thing I want to note here. It might not be on those instructions. So what do we have here for name? Is a simple name is we have a substituent. It's on the one place of the carbon, but we don't have to label it because it automatically assigns it as one. So we would call this butyl cyclohexane. hexane, because there's 6 carbons in there, right? We call it butyl cyclohexane. Okay, so if we change, so that could be any length until the substituent gets longer. Okay, when the substituent gets longer, we now have 5 carbons on this side of the equation and 4 carbons on that. So that means the pentyl group is now the parent. So we have to name it pentane. So we're going to name this 1-cyclobutyl pentane. Notice I added the YL because it's now a substituent. Okay, same rules apply. It's just you look at the longest thing of carbons, either that are in that ring or that are in the longest straight chain. Okay, questions on that? Okay, so now we have what we can do if we have 2 of the same substituents on the ring, and we know if we have 1 substituent on the ring. So let's put 2 things on the ring that aren't the same. Okay, so we'll make sure that we can understand that. So if we had that and that, we already know that that's dimethyl cyclopentane, right? Because we have 2 methyl groups on there. And we would start numbering from 1, 2, and 3 because it doesn't matter. So we would have 1,3 dimethyl cyclopentane. We would need more information to assign cis and trans. There is no 3D drawing on here, so we can't assign cis and trans. So that would be, the way we would name that would be 1,3 dimethyl. But what if we had this? Okay, so we have a methyl substituent, but we have an ethyl substituent. Which one's number 1? Well, since the next step we'd have to do anyway is alphabetize, what we're going to do is we're going to alphabetize our substituents and number the lowest alphabetized one in position 1. So we get both number and alphabetization in the same rule. So that's pretty cool. So this is going to be 1, 2, 3. So this would be 1 ethyl, and we have to put the 1 because we have more than 1 number. Methyl dash 3 dash methyl cyclopentane. Okay. So this would make it, now, are they on the same side or opposite sides of our ring? We don't know. We don't have enough information here, so we will not have to assign cis or trans. But if they were drawn with 3D perspective, you would be requested to ask whether they were cis or trans.
Wait, so 3?
Huh? No, this is 1, 2 ethyl. So it's lower in ethyl. E comes before M alphabetically. So that puts this at the 1 position. So 1 ethyl. And then 2, 3 methyl. If we labeled it the other way, 2, 3, 4, that would be a higher number. So if we went around the other way, it'd be a 4 methyl, and that's breaking a rule. We're just adding to the rule. We're not breaking it.
So you base it off of the alphabet of the
Yes, for cyclogroups. For cyclogroups, it's alphabetical. Okay. Let's see. Questions in the chat there. For more than substituents, we have to do a slightly modification of that. We go in alphabetical order and assign the number 1 position to minimize the total number. Okay, so what that means is now if you have an ethyl group and a methyl group and a methyl group, and it turns out to be fewer numbers to neighbor through the 2 methyl groups, you might have to do that. Let me show you an example of that. Is 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay, so we have an ethyl group on top here we have a methyl group, and we have a propyl group. So if we wanted to alphabetize them, this ethyl group would be first. But what do our numbers look like? 1, 3, 4. So this is where we have to go, okay, let's go back to our numbering scheme first. We number first, then alphabetize. So we're actually going to change these numbers to be 1, 2, 3, and then 4. Why? Because we're doing the numbering first. When we have more than 2 substituents, you do numbering first. And you have 1, 2, 4 versus 1, 3, 4.
But it says site now.
Cite in alphabetical order, find them, and then number.
Oh,
Okay. So that means that we would number it this way, but we'd still put the substituents in alphabetical order. So of these, this is a propyl group, this is a methyl group, and this is an ethyl group, which means our name would start out 4-ethyl because the ethyl group has to come first. But the ethyl group is now assigned to the number 4 because we numbered first with more than 2 substituents. It's a little and if we think about it, you know, the reason it's with 2, there's no, they would both be numbered at the same number either way. And so alphabetization wins out. Here we have numbers first. We always did the numbers and then alphabetization and then di and tri and tetra. We're gonna have the 4-ethyl. We're gonna have, let's see, M-N-O-P. So M comes first. Yes, I expect you to do that in the exam. Methyl dash 1 propyl cyclohexane. Okay, so do we see how this is just slightly different from 2 substituents? With 2 substituents, you were going to name them 1, 3, or 1, 2, no matter what. But alphabetization tells you you have to do, you can name the lower alphabet one a lower number. Here we're doing our numbering first, but when we write out our final name, we put them in alphabetical order. Okay? Does that clarify that? Okay, so let's do a couple more examples. Let's do that. Okay, so what's our parent? Cyclohexane. Okay, and what are our substituents? So we can say dimethyl, right? We can dimethyl. We just have to figure out where the numbers are. And then we have a butyl. Okay, so now let's try to find the lowest set of numbers we can have. And we're going to go here. So if we started here, we have 1, 2, 3, 4. If we started here, we'd have 1, 2, 3, 4. If we went around the other way, we have 1, 2, 3, 4. Oh, it's not going to go that way. It's too many numbers already. Okay, so we have 2 choices to decide from of our numbering system. Are we going to number it the blue set of numbers, the first set of numbers that are blue on my screen, or the second set of numbers that are green on this? Blue, because in blue we get 1, 2, 4. In green we get 1, 3, 4. So it's lower number. So that assigns our functional groups. I mean, that assigns our substituents, okay? So that means it's not the green, so we can take those out. So now we have a methyl group on the 1, a methyl group on the 2, And the butyl group is now on the 4. Okay, so now we have all our components. We have them all correctly assigned by number. Let's put it all together. We put it all together. We're going to have, let's see, butyl comes first. So we're going to do 4 butyl. 1, 2, dimethyl.
Get that first.
Cyclo, remember we're running them all together. There's no gaps, no capitalizations. I'm going to have to actually hyphenate and have hexane down here, sorry. Hexane, okay. So we followed every single rule. This is why I like using scratch paper on exams and stuff, because then you can just get all your substituents down correctly and then sort them out at the end. All right, I want to do one more example. And I'm going to, I don't want to erase this one. Let me do one more example on, okay, I'm going to erase it. Oh, I'll do it here. Because we're going to follow this rule again. We're just going to do one more thing. Note to self, add one more slide to here so I can add another example. Okay, my new example is going to be okay, so right away, I'm cheating because I have a methyl substituent, an ethyl substituent, and a butyl propyl substituent. Actually, that's supposed to be a butyl. There we go. Butyl substituent. Okay. Oh, those aren't the same as the other one. But anyway. Okay, so what do we do first? So we do our parent first, right? So let's do 1, 2, 3, 4, 5, 6, 7 carbons in that ring. So that's cyclo, the new word, cycloheptane. Right there, and we have an ethyl substituent, a methyl substituent, and a butyl substituent. Okay, so how do we assign these? Butyl's lowest, ethyl's second, methyl's first, but we have to number first. So we're going to number from the lowest first 1, 2, 3, and 4. Or we could do it 1, 2, 3, and 4. Okay, is that first set of numbers closest to the carbons the right way to number it? Right, because in our first set of numbers, it would be 1, 3, 4 would be the numbers on our substituents. In the second set, it would be 1, 2, 4. So we have to name it on that second set. So it's going to be 1, 2, 4. So now we can assign our substituents, and our 4 is on the butyl, our 2 is on the methyl, and our 1 is on the ethyl. Okay. That being said, we're now ready to fill it out completely and write this on your notes at home. Let's see. Butyl comes first. So it's going to be 4 dash butyl dash 1 dash ethyl dash 2 dash methyl, no space, no gap, no dash, cycloheptane. All right. Cool. So, okay. Questions on naming cyclohexane? So we have straight chains, we have rings. We know there's a top and a bottom of a ring with cis and trans. Now let's talk about putting 2 rings together and really, really making it, getting to some interesting looking structures. So the first thing we're going to do when we put 2 rings together is we have to assign a few things. And so the first thing I want to assign is, what do I mean by two rings together? Okay, so I'm going to use an example here that says, okay, I have a cyclobutane. I'm going to put another thing on there. So now I have two cyclobutanes. This is now a bicyclo compound. There's two cycles, okay? So we have to identify some parts of these two cycles first. So the first part of the cycle I want to do is the Bridgehead carbons. Bridgehead carbons are defined as the ones that they're common to both rings. Notice these two carbons out here are independent of these two carbons. Only those ones in the middle are associated with both rings, okay? So those are bridgehead carbons, okay? That means a bridge is the other carbons. So we would say there's going to be one bridge here, which is those other one bridge here, sorry, one bridge here, one bridge here. But actually, it turns out that there's a bridge in between those two carbons there as well. So each of those counts as a bridge, okay? So this can be, oh, sorry, that makes it fused. Let me draw a different structure. And let me assign those bridgehead carbons again. This is a bridge. This is a bridge. Do we see how we have two rings here? We have a ring on this set here. And then we have a ring on the other side there. Okay. So now when we assign our bridges, we have one bridge here, and one bridge here. Okay. So in the one right here, we have three bridges. So that means we have what we call a fully bridged cycloalkane. In here, we only have two bridges. We call those fused, but we number them in a similar fashion. Okay, so let's figure out how to name these things. Okay, so the rules are identify the parent hydrocarbon. In this case, the largest number of carbons in both rings. Remember, when we named a cyclohexane, it was because there were 6 in that ring. If we have a cyclo ring, but it's in 2 different rings, we call it bicyclohexane. So we're going to name it bicyclohexane. Okay, so we're going to have to figure out the largest number of things possible. So let me draw an example right here. 1, 2, 3, 4. Okay, so how many total carbons do we have in this bicyclo compound? So we're gonna, I always start by circling the bridgehead carbons so you know where they are. Right here. So we're gonna have 1, 2, 3, 4, 5, 6, 7, and 8. Notice you don't count any of the bridgehead carbons twice. So we only have a total of 8 carbons in our bicyclo compound, which makes this bicyclooctane. Bicyclooctane. All right. So that's the way we get to our parent name. Okay, what's the next rule? Identify the bridges. Okay, so since we've identified these as our bridgehead carbons, that means this is a bridge, this is a bridge, and this is a bridge, right? Because they are all attached to those bridgehead carbons and they are all unique. Okay, so that means our bridge A has 2 carbons in it. Our bridge B has 1 carbon in it. And our bridge C has 3 carbons in it. Do we see that?
Why does bridge B only have 1 and not 3? Are you not including the bridgeheads?
We do not include the bridgeheads in our counting of the bridges. So notice over here, A just has A, 1, and 2 for a total of 2.
I've been unmuted so many times.
C is on the B And then there's 1, 2, 3 on this C bridge. Does that make sense? All right,
Yes, thank you.
perfect. Okay, so now we have the number of carbons in each bridge. We have a total number of carbons in the bicyclo compound. Now let's name this. Okay, how are we gonna, oh, this is crazy. Well, we're gonna name it by the number of carbons in each bridge, but we're gonna name it by the number of carbons in each bridge from the highest to the lowest. So what does that mean? That means that we're gonna have the number 3 assigning this side right here, the number 2 assigning this side right here, and the number 1 assigning the center one here. So what does that look like? Well, we have a special notation for this. We're gonna say, because it's a bicyclic compound, we want to identify each of the bridges, how long they are. So we're gonna say 3 dot, 2 dot, 1 bracket bicyclo cyclooctane. I guess we can drop one of those O's. Okay. So when we draw this, we say, okay, wait, hold it. I have a bicyclo compound. I have 3 carbons in one of the bridges. I have 2 carbons in another one of the bridges, and I have 1 carbon in the other bridge. So wait, hold it. We have the difference between bridged and fused, right? The fused didn't have that 3rd bridge. So in the case of fused compounds, this is a 0 right here. So we'll have 2 carbons in this bridge, a bridgehead, 2 carbons in this bridge, and 0 carbons in that bridge. Ooh, that changes the name then, right? So our name's going to be 1, 2, 3, 4, 5, 6 carbons total. So it's cyclohexane. But the bridges are 2.2.0. Cyclohexane. Do we see why it's hex? There's only 6 carbons.
Did we get bicyclo?
I'm sorry, you're right. Bicyclo. Thank you. Bicyclohexane. Bicyclo tells us we have 2 rings. The brackets tell us that each bridge has assigned a certain number of carbons. The first bridge is 2 carbons. The second bridge is 2 carbons. And the last bridge is 0 carbons. So that's the bridgeheads being bridged to each other. 0 extra carbons. Okay, so now if we go back and look at this 3, 2, 1, we see 3, 2, and 1 carbons in each of those bridges. Okay, does that bracket and numbers make sense? Okay, so I'm going to name a couple of those, and that's where we're going to stop with, we'll do this. And then we're going to, this is where it'll end for the exam, bicyclo nomenclature, okay? Bicyclo, everything up to bicyclo nomenclature, plus chapters 1 and 2 and 3, okay? So let me go through another couple weird ones, just to make sure we got all these things right. I want to do 2 kind of weird ones, because I also have to tell you about substituents. And then, okay, these are my 2 weird ones, and I want to do this as a substituent. Oh, no, I need to change that one. Let me change this one. Okay. All right, so let's name this first weird one first. Okay, so how many carbons are in that, both of those cyclo compounds here? One way to think about it is, well, let's just start labeling them. 1, 2, 3, 4, 5, 6. That's a substituent, so we don't count that. 7, 8, 9, 10. So our base name is bicyclodecane. Decane. Okay, and we have a substituent here. So substituents are really weird on bicyclo compounds. Now, remember, in bicyclo compounds, we number our bridges by the number of carbons in each bridge, and we put the number of carbon, the bigger number first. So let's do that part before we talk about the substituent. So if we have that, what are our bridge numbers going to be? We have a 1 here. We have a 1 here, we have a 3 over here, and we have a 4 over here. So we're going to have 4, 3, 1 as our numbers. 4 dot 3 dot 1 bracket. So those are our numbers. But when we name bicyclo compounds, we start with the largest ring first from a bridgehead carbon. So when we number this, we have to go from starting at this bridge, starting from this bridgehead carbon or this bridgehead carbon. Okay, so if we're starting to number from those bridgehead carbons, we have to go around the largest one first because the largest number comes first. So we're going to go 1, 2, 3, 4, 5, 6. So where do we go next? If we started with the largest one, we're going to go to the next largest one, the 3, 7, 8, 9. And we don't count our bridgehead carbon again. So that means our last position is 10. Okay, so that's how we number something around here. But we have to number from the largest through the second largest through the smallest. But we have a substituent on here. Can we number this a different way to get that substituent on a lower number? Well, if we break the rules, we can just say, let's do this. Oh, well, 1, 2. We could just put on the 2 here, right? No, we haven't gone around the longest one first, okay? So since we didn't do that successfully going around the other way, let's go around this way now. Starting with 1, 2, 3, 4, 5, 6. And now this would be 7, 8, 9, and 10. So 7 is the lowest number we can have for this substituent. It would have been 9 if we named it the other way, but it's 7 when we number it this way. So bicyclos, you always number from a bridgehead carbon around the longest bridge to the next bridgehead carbon, around the next bridge, not renumbering the bridgehead carbon, and then your last remaining carbons are on that third bridge. And then you try to number it in such a way you get the lowest number substituent. Okay, questions on that? I'm right here at 12:15, sorry, 12:15. Okay, if you want to stay behind and ask questions, please do. Of everything up to bicyclo nomenclature is on exam number 1. See you on Monday.
That's Monday, right?
Test on Monday. I will be here live and in person. Your dog. The exam can be at the testing center or at or online. It will be offered online until COVID numbers go down. So yeah, you have the option of live or online. Okay, I will send an email out to that effect as well. All right. All right, I'm gonna stop recording.